Hey everybody, this is Thomas from my channel Astronize, and today I would like to make a short Python video about something that I almost forgot, namely the partial solar eclipse that will happen on the 29th of March 2025. So if you watch this video today on the 28th, it is basically tomorrow, and if you watch it later, well, I'm sorry, you missed it. The partial solar eclipse looks something like this from here. If image from a NASA satellite. So of course we don't see the sun from Earth with the naked. Okay, with the naked eye you should never look into the sun, but this kind of sun picture is from a dedicated filter, and we have here the moon that is covering a part of the sun. So this is just partially covering it, so we will not see the corona, also it will not cover the entire sun. Quick note, if you would like to take a look of this partial solar eclipse, please be aware to never look into directly with the naked eye or with binoculars or telescope or something like that. Always use certain certified glasses that can be used for solar eclipses. So, but anyway, enough words of warning. This is something that will happen tomorrow. Now, if we are taking a look here in Stellarium, we can also simulate the path. We click here on the sun, for example. I have here my hometown, here Stuttgart in southern Germany. And if I simply change the date time to tomorrow, no, this is April, tomorrow, and go back in time a little bit, you see already the moon approaching the sun. But I'm going back in time, and we see here at around 12 o'clock local time that the moon is covering the sun. So yeah, this will be for like over an hour, I think an hour 30 or so, covering the sun. Now, when is the sun being covered by the moon? This is a value we need now for our Python code. Well, we see here if we click on the sun on the left side, where is it? I think this, here it is, the apparent diameter. We have a diameter of around half a degree. So a quarter of a degree is the radius, yeah, and therefore also round about the quarter of a degree is also the radius of the moon, which means that if the centers of these two objects, of the sun and the moon, if this is smaller than half a degree, we have some kind of coverage, of the moon covering the sun. Enough of the theory, enough of this small introduction. I would say we switch directly into Python and see how we compute this stuff. Well, some of you may know this already. This is my Astronize YouTube tutorials repository, and I just pushed a code on this repository, a code that, frankly speaking, I prepared yesterday evening. So you have to simply click here on compressed cosmos, and then we have here the script compressed cosmos underscore sun moon distance. We click on this as well, and then we have here the small batch open in Colab, and it directly redirects us to Google Colab, where we can now connect to an instance and then execute the code. Of course, there will be a warning saying, is this code maybe suspicious? Be aware of this. You can check the code. There is nothing suspicious in it at all. And since last time we introduced AstroPy, I would like to continue with AstroPy also in this video and maybe also the other videos. So we have here, we will here not compute the percentage of the coverage, but the angular distance between the sun and the moon, and converting it to some kind of percentage of these two circles in the sky. That's maybe a good homework for you to adapt the code, adjust it, and learn something. Now here in the very first cell, we are introducing, of course, importing AstroPy, and we have here the latitude and longitude values of our location. Now these are the values approximately for Southwest Germany, where I live. And then we have a small function to compute the separation of the sun and the moon. And here's just a function where we simply take the longitude, latitude, and also the height. You can adjust it as well, but I put it here to 0 meters. The Earth location from AstroPy. Then we take the time. We expect a date time format. I will show you also in a second how and why. And then we simply compute the sky coordinates for the moon and the sun and use then the function separation and return it in degrees. And that's basically it. This is all we need to compute the angular distance or separation between the sun and the earth. So let's execute this first cell here. Takes a few milliseconds, and then we can go to the date time part where we have to define three things. Here at the very bottom, the start and the end time as a date time object, but we have here to introduce some additional information what time zone we are speaking of. And here we don't have to work only always in UTC, because then you have to convert from your local time zone, but you can write down your local time zone if you know its name. In my case, it's Europe/Berlin, and then it will consider the difference between UTC and my time zone where I'm living. So we can execute this script as well. Afterwards, we have just a while condition where we just iterate from the start time to the end time in 60-second steps, which is defined at the very end of the cell here. We execute this script here, and then the angular distances are then being computed, so that now we have two arrays, one with the date times and one with the separation angle between sun and moon, of course, based on the center of each object. This takes a few seconds, and then afterwards we can plot the results as well. And what I'm doing here is simply plot the angular distance versus the date time, but then also adding a horizontal line at 0.5 degrees. This is what I just said in Stellarium. This is, like, I would say, the threshold where the coverage starts, so where the moon is starting to cover the sun. This is not exact in the exact value. This is maybe a good case homework for you to figure out how with AstroPy or other tools you could consider the apparent diameter of an object in the sky. So apparent diameter is a good keyword, I would say, and then figure out some kind of method or algorithm how two circles, depending on the coordinates, what is the percentage of the coverage of these two circles. There is literature around, but I think this is like a very good starting point to at least compute the vectors of the center of both objects, and then afterwards considering also the apparent diameter for you. You can just start with simple circles and with a half a degree diameter, so this may be a good starting point. But let's have a look here in this plot where we see here the angular distance versus the time. The horizontal line here is like the coverage, starting coverage or ending coverage of the moon sun relations, let's say. And this is a mistake. It's not the UTC date time, it's the local date time here in my case. It's just a small copy paste from my last video. But we see here that the coverage starts at around 11:30 and it goes to almost 1 o'clock in the afternoon. So this is like a very short time where the things are where the moon is covering the sun. Now, if I look outside the window, it looks kind of nice today. But considering the weather prediction for tomorrow, it is, as always with astronomical events, cloudy and most likely rainy. Yay!